So now we will begin discussing precipitation processes. How do tiny cloud droplets grow large enough to become raindrops that fall out of clouds and make it to the ground? If the raindrops evaporate before reaching the ground, they're called virga. So we'll also be talking about how ice crystals grow in size to become snowflakes or snow pellets called grapple. So to start out, here is a figure illustrating typical sizes of raindrops, cloud droplets, and cloud condensation nuclei, or CCN. Remember that from when we were talking about clouds? As you can see, the typical cloud droplet has a size of 0.02 millimeters, and that size corresponds to the diameter. So typical cloud droplet will have a diameter of 0.02 millimeters, and you see it's pretty spherical shape, right? It kind of looks like a ball, okay? On the other hand, cloud condensation nucleus size, whether it be a smoke particle, a dust particle, a salt particle, is only 0.0002 millimeters in diameter. So its diameter is 1/100th, right? 1% of the droplet of a typical cloud droplet. These are just average sizes, okay? It can vary for these different shapes. On the other hand, the raindrop is usually 100 times the diameter of the cloud droplet. And again, raindrop in this figure looks spherical shaped. Okay, I'll tell you that's one of the shapes it can look. It can also look like a hamburger bun. Okay, contrary to common public opinion, raindrops are not tear shaped. Okay, so then if you remember your geometry from Algebra 2, okay, you'll remember that the volume of a sphere is 4/3 pi r cubed, r being radius. So if the tip, and the radius is just half the diameter, so therefore if the diameter of a raindrop is 100 times that of a cloud droplet, the radius is 100 times that of the raindrop is 100 times that of the cloud droplet. So that means the volume of a raindrop is, on average, 1,000,000 times the volume of a cloud droplet. Therefore, it takes 1,000,000 cloud droplets to form one raindrop. Okay, so then you might be wondering, well, how in the world can these cloud droplets grow so much, to become raindrops, right? If the raindrops are so much larger, well, we'll be talking about it. And the largest raindrops can be 5 to 6 millimeters in diameter. Those raindrops would fall over the tropics. Okay. But generally, the raindrop is not going to become larger in diameter than about 6 millimeters, because eventually if it becomes large enough, it will break up easily on its own. Its surface area becomes too much for it to handle. It also will make contact with other drops and break up that way. Okay, just for reference, diameter of a human hair is about 0.04 to 0.12 millimeters, depending on the person. Okay, some people have thinner hair. Some people have thicker hair, okay? And for someone like myself, my hair is really thick, so I have to get special conditioner or else it knots up easily, okay? So keep in mind the relative sizes of the condensation nuclei, the cloud droplet, and the raindrop as we go forward. So, some clouds can begin producing rainfall only 1/2 hour after being born or formed. And that's not long enough to from cloud droplet growth via condensation alone. Okay. Yes, as vapor molecules begin to condense onto droplets, they can grow larger. Okay, but as you have more condensation occurring on these CCN, but that process alone, condensation, growth of cloud droplets via condensation, is too slow to form these large raindrops. Okay, it would take hours and hours, up to a day, okay, to form raindrops from that process alone. And as you can see, some clouds start producing rainfall not very long after they form. Okay, So there has to be some other elements to the story. So, in order to understand how precipitation forms, we have to look at the clouds from two different perspectives. We can look at warm clouds that have their tops warmer than minus 15 degrees Celsius or 5 degrees Fahrenheit, in which case precipitation development in those clouds is from the collision coalescence process, which refers to a larger cloud droplet colliding and coalescing, attaching smaller cloud droplets to it. And in this process, droplets can form very quickly, okay? Generally, clouds that have tops warmer than 5 degrees Fahrenheit are only going to be composed of liquid water, okay? Not ice crystals or solid water, okay? Remember, like we were talking about, even though, yes, water freezes at 32 Fahrenheit, as the size of the water droplet becomes smaller, it actually has to be even colder to turn into ice. So even in clouds down to 0 Fahrenheit, they're mostly composed of liquid droplets, not ice crystals. On the other hand, when the tops start to get colder than minus 15 degrees Celsius, 5 degrees Fahrenheit, that's when you start seeing significantly more development of precipitation from the Bergeron ice crystal process. And that can form snowflakes and snow pellets. Okay, so the type of precipitation development depends on the type of cloud, how warm the cloud is. Now, we're going to start talking about warm clouds in the collision coalescence process, which can form raindrops. And by the way, this is common over the tropics and the mid-latitudes in the summertime. Okay, Bergeron ice crystal process is more common in the polar regions and actually the mid-latitudes for much of the year. Okay, so in order for the collision coalescence to be process to be effective, some of the cloud droplets have to be larger. Okay, so in clouds with tops warmer than 5 degrees Fahrenheit, the collision coalescence process can play a significant role in producing precipitation. And to produce the many collisions needed to form a raindrop, some cloud droplets have to be larger than others. Okay, there has to be a variation in size of droplets. The larger droplets, how do they form? Well, they might form on larger condensation nuclei like salt particles or through random collisions of droplets. Studies also suggest that the amount of turbulent mixing between the cloud and its drier environment outside of it may play a role in producing larger droplets. Now, as the cloud droplets fall, the air resists the falling drops. The amount of air resistance depends on the size of the drop and on its rate of fall. The greater the speed of the falling droplet, the more air molecules the drop encounters each second, and the more air resistance on it. The speed of the falling drop increases until the air resistance equals the pull of gravity, or force of gravity. At this point, the drop continues to fall but at a constant speed known as terminal velocity. Recall from physics, terminal velocity is the basically the maximum speed of a falling object, okay? Because larger droplets have a smaller surface area to weight ratio than smaller drops, they must fall faster before reaching their terminal velocity. Hence, larger drops fall faster than smaller drops. So the larger the droplet, the faster it can fall, okay? Because the faster it has to, the greater its speed has to reach in order to balance out the force of gravity on it. Large droplets overtake and collide with smaller drops in their path. When they collide, that's collision. But when they merge and they overtake the smaller drops in their path, stick together, that's coalescence. Okay, merging of cloud droplets by collision is called coalescence. Laboratory studies show that collision does not always guarantee coalescence. Sometimes the droplets actually bounce apart during collision. Okay, sometimes they break up. The forces that hold a very small droplet together, surface tension, are so strong that if the droplet were to collide with another tiny droplet, chances are the droplets would not stick together. Coalescence appears to be enhanced if droplets that collide have opposite charges, opposite electrical charges. Recall from physics and chemistry that opposite charges attract, okay? And that can be true for relationships of humans, okay? But it might also not be, it might be the other way, okay? Sometimes people that have similar personalities and interests also can attract, okay? So to illustrate the collision coalescence process, here's a diagram, and this diagram really does a nice job illustrating how you need a larger cloud droplet for this process to be effective. On the left, part A of the figure, you have small cloud droplets, and so basically the droplets are composed of, or the cloud is composed of droplets of uniform size. See, they're all the same size. And the droplets are not likely to collide as much because they have the same size, and so they all fall at the same speed. And because they're small, they fall slowly, okay? So they're small cloud droplets, they're uniform size, so they're falling very slowly. And if that happens, if they're falling at the same speed, right, they're not going to be able to run into each other. They're going to stay the same distance apart, okay? And even the droplets that do collide frequently do not coalesce because of the strong surface tension holding together each tiny droplet. On the other hand, in a cloud composed of different size droplets, okay, you have a lot of small droplets, but you also have a few larger droplets. Different story there. The larger droplets fall faster than the smaller droplets. Although some small droplets are swept aside, some small droplets collect on the larger droplet's forward edge, as well as on the droplet's backside. And as the larger cloud droplet makes contact with and collides with, coalesces these smaller droplets, it grows larger in size. Then it begins to fall faster, and so it can attach more droplets as it continues to fall because it's growing larger in size, right? Now, updrafts are really important to enable droplets to grow larger. It turns out there's a relationship between updraft speed in a cloud and the size of the raindrops, in fact. Rising air currents are updrafts. That's all they are, okay? And they allow a droplet to move upward and grow in size. Stronger updrafts permit the droplet to be in the cloud longer and grow larger. And the interesting thing is, updrafts can help suspend or even cause a droplet to rise. So even though the droplet has a natural tendency to fall, right, due to the force of gravity, especially as it grows larger, it's going to fall faster. If you have a really strong updraft, that'll help keep it suspended in the cloud, okay, until it becomes large enough where its terminal velocity, its fall velocity, exceeds the cloud updraft velocity, in which case it will descend and continue to grow as it falls, as it coalesces with other droplets, okay? If the cloud droplet velocity and the updraft velocity are the same, right, then they'll cancel out, and so it would just appear suspended at the same elevation, okay? Illustration of the importance of an updraft in the cloud, and this is for like a cumulus congestus, or more like a cumulonimbus cloud, because remember, cumulus congestus clouds don't really produce rain, okay? But a cumulonimbus cloud can form from a cumulus congestus cloud. So you have this cumulonimbus cloud with an updraft speed of 6.5 meters per second, or for us Americans, 14.5 miles per hour. Okay, 15 miles per hour, that's a light to moderate sprinting speed, right? And a cloud droplet with initial diameter of 0.1 millimeters is rising. It's very small. It's rising, and then later falling through a warm cumulonimbus cloud. it can grow by collision and coalescence and emerge from the cloud as a large raindrop. Suppose the cloud droplet is caught in this updraft. As the droplet rises, it collides with and captures smaller droplets, both on its forward edge and backside, until it reaches a size of about 1 millimeter in diameter. Okay? At this point, the updraft of the cloud is just able to balance the pull of gravity on the drop. So the drop remains suspended at this height until it grows just a little larger. Once the fall velocity of the drop is greater than the updraft velocity of the cloud, okay, the drop slowly descends. As the drop falls, some of the smaller droplets get caught by it and are swept aside, but there's also larger cloud droplets captured by the falling drop, and it grows larger, and as it grows larger, it falls faster. Okay? By the time the drop reaches the base of the cloud, it will be a large raindrop with a diameter of 5 millimeters or greater. Because raindrops of this size, the larger droplets tend to fall faster and reach the ground first before the smaller raindrops. Typically, the larger raindrops occur at the beginning of a rain shower from these warm convective current clouds. Okay, so if you ever if you've ever experienced a cumulonimbus cloud producing rain, often when the rain starts, it's very heavy and the raindrops are larger, right? Then maybe the speed of the falling rain decreases, right? It's not as heavy because then the smaller droplets fall and they're not falling as fast. Okay? So there are important factors for droplet growth in warm clouds. The most important factor in the production of raindrops from warm clouds is the cloud's liquid water content. Okay, you have to have liquid water. The more liquid water in the cloud, the larger the drops can grow. But in a cloud with sufficient amounts of liquid water, other significant factors include the range of droplet sizes, right? You need larger drops, okay, for this collision coalescence process to be effective. If the droplets are uniform size, you're not going to be able to form very large raindrops. Thickness of a cloud is an important factor. Thicker clouds allow for larger droplets to form, right? If the cloud is very thin, like a nimbostratus cloud, it's not that deep, then the drop's not going to be able to grow, have as much height to grow, right? Updrafts of the cloud are important. Generally, the stronger the updraft speed, the larger the raindrop size. Because the smaller the updraft speed, the larger the drop has to grow in order to actually start falling. Okay? So nimbostratus clouds do not have very strong updraft speeds, and hence they don't form very large raindrops compared to cumulonimbus clouds. Okay? And electric charges of the drop are important because this is a factor that can help actually enable the drops to stick together once they collide, okay? Opposites attract. Now, what about the Bergeron ice crystal process, okay? So, the collision coalescence process deals with liquid drops in clouds, but in the Bergeron ice crystal process, ice crystals and liquid droplets must coexist at temperatures below freezing. Okay? So somewhat surprisingly, in the cold air of a cloud just above the freezing level, right, almost all of the cloud droplets are still liquid water. Or almost all of the particles of the cloud are still liquid water. Okay? Water droplets existing at temperatures below freezing point, 32 degrees Fahrenheit, 0 degrees Celsius, are called supercooled droplets. At higher and higher levels, ice crystals become more numerous as temperatures decrease, but are still outnumbered by water droplets, even above -4 Fahrenheit. Okay? So at temperatures above -4 Fahrenheit, there are still more liquid droplets than ice crystals. Okay? Do you know what temperature the cloud has to drop to in order for it only to be composed of ice crystals? Hint, where do the Fahrenheit and Celsius scales meet? They meet at minus 40 degrees, right? Minus 40 degrees Fahrenheit equals minus 40 degrees Celsius. This figure shows the distribution of ice and liquid water in a cumulonimbus cloud, right? Here's the high, right, vertically exaggerated cumulonimbus cloud. Here's the anvil top. So what happens is once the cloud is made only of ice crystals, owing to how ice crystals scatter light differently than water droplets, when the cloud is made only of ice crystals, it begins to take a fuzzy appearance. And we call part of a cloud made only of ice crystals glaciated. Okay, glaciated, right? Think of glacier, right? Ice. So what you see is that below the freezing level, the cloud is only made of liquid water. Then there's a mixture of ice and water above the freezing level until you get to about minus 40 degrees Celsius. Okay. So, how does this Bergeron ice crystal process work? Well, in order for it to be effective, ice crystals are required to form, and in order to form, ice crystals need a nuclei called an ice nuclei, IN. Okay, remember how in order for droplets to condense, right, for vapor molecules to condense onto, or to do that, they need a CCN, cloud condensation nuclei. Well, in order for vapor molecules to deposit into ice crystals, they need a nuclei, and it's called an IN or ice nuclei. And ice nuclei are less abundant than cloud condensation nuclei. Why? Well, although there is some uncertainty regarding the principal source of ice nuclei, it's known that certain clay minerals, bacteria and decaying plant leaf material, and ice crystals themselves are excellent ice nuclei. And it tends to be that there's less of these ice nuclei than cloud condensation nuclei. Okay, there's more specific and rarer found surfaces that can form as ice nuclei. Okay, part of the reason is because particles will serve as an ice nuclei if their geometry resembles that of an ice crystal, but that tends to be rarer than the particles that can vapor molecules that can condense onto liquid that can condense onto CCN to form liquid droplets. Okay. Again, the smaller the droplet, the lower the temperature required for freezing. Okay. Now, in the Bergeron ice crystal process, supercooled water droplets surround each ice crystal. Okay, so around an ice crystal there'll be water droplets at temperatures below freezing. Okay. The air is saturated. Okay, remember in a cloud the relative humidity is 100%, but more water vapor molecules will leave the liquid droplet than the ice crystal. Recall that the saturation vapor pressure is lower for ice than for liquid water. Okay. The air is saturated in a cloud, meaning the number of molecules leaving the surface of a droplet in ice crystal must equal the number of molecules returning. But because more water vapor molecules are around the liquid droplet than the ice crystal, the liquid droplet has a higher saturation vapor pressure, and that causes water vapor to diffuse to the ice crystal, and the ice crystal grows at the expense of the droplets. Okay? So in a cold cloud, there's many more liquid droplets than ice crystals, even at low temperatures. And initially, neither the tiny liquid or solid particles are large enough to fall as precipitation. Then how does snow or rain form? From this fact that the water vapor will diffuse to the ice crystal, okay? Due to a difference in saturation vapor pressure around these two surfaces, okay? Figure from the book, temperature minus 15 degrees Celsius, 4 degrees Fahrenheit. This is a saturated environment. Here you have a liquid droplet on the left and an ice crystal on the right. The water in a saturated environment, the water droplet and ice crystal are in equilibrium. The number of water molecules leaving the surface of each of these particles equals the number returning. But the greater number of water vapor molecules above the liquid produces a greater vapor pressure above the droplet than above the ice crystal. Okay, again, there's saturation. So in this case, the vapor pressure equals the saturation vapor pressure. Okay. Notice, right? You clearly see that around this liquid droplet, there's more vapor molecules in its vicinity and the same volume around it than for an ice crystal. That has to do with stronger bonds in the ice crystal, right? Less molecules leaving the ice crystal and becoming vapor, sublimating than above the droplet, evaporating. Okay. So then what happens is water vapor molecules leave the vicinity of the liquid droplets, okay? So the greater number of water vapor molecules around the liquid droplet causes water molecules to diffuse from the liquid droplet toward the ice crystal. That causes the ice crystal to absorb this water vapor. Basically, the water vapor deposits onto it, and so the ice crystal grows larger. But then you're taking away vapor molecules around the water droplet, so now its evaporation exceeds the condensation, right? And therefore the droplet becomes smaller. The droplet grows smaller while the ice crystal grows larger, okay? And so the ice crystals grow at the expense of the surrounding water droplets, okay? Now, what types of precipitation result from the ice crystals falling? Well, then you have to start thinking about once this ice crystal falls, what happens, right? So we're starting to understand how it's going to grow larger initially, and when it grows larger, it's going to fall faster. Then what can happen as it falls? Well, a few different things can happen, okay? So here are three fates of the falling ice crystal. A. Falling ice crystals might freeze supercooled water droplets directly on contact. That's called accretion, producing larger ice particles. Okay. So, for accretion, the ice crystal falls and it freezes these supercooled water droplets directly on contact. Okay, and then the ice crystal grows larger. That can form graupel or snow pellets. Accretion can form graupel or snow pellets, kind of like small hail pellets or small hailstones. The falling ice crystals might collide and fracture into many tiny ice particles, and then they might actually sublimate, right, because they're so small. Or the falling ice crystals may collide and with not supercooled droplets, but other ice crystals and stick to them. Okay, this is kind of like the coalescence for ice crystals. This is aggregation. Falling ice crystals colliding and sticking to other ice crystals, and this forms snowflakes. Okay, this is how snowflakes form. Ice crystal grows larger at the expense of surrounding supercooled droplets. Then ice crystal collides with other ice crystals and grows. Okay. If the snowflake melts before reaching the ground, it continues its fall as a raindrop. In fact, much of the rain falling in the mid-latitudes, and especially the high latitudes, even in summertime, begins as snow. Okay, so for the high latitudes and much of the mid-latitudes, often the precipitation begins as snow. Okay, and then melts into rain, especially for cumuliform precipitation, that originates from cumulonimbus clouds. Okay. Have you heard of cloud seeding? Talk about how to get the clouds to produce more rain. The idea in cloud seeding is to inject clouds with small particles that act as ice nuclei. So the ice crystals will grow large enough to form rain. Okay. The first ingredient in any seeding project is the presence of clouds. Seeding alone does not generate clouds. So if you try to release ice nuclei or particles that act as ice nuclei into open, clear air, it's not going to form clouds. Okay, so you can't do that, whether it be from an airplane, whether it be from a helicopter. You need a cloud. Okay. Now also, at least a portion of the cloud, preferably the upper part, must be supercooled because cloud seeding uses the Bergeron or ice crystal process to cause the cloud ice particles to grow. Okay, and generally you need a low amount of ice crystals. Okay, the ice crystal process is also called the Bergeron process, named after the meteorologist Bergeron. The idea with cloud seeding is to find clouds that have too low of a ratio of ice crystals to supercooled droplets, and then to add enough artificial ice nuclei so that the ratio of ice crystals to droplets is optimal for producing precipitation. And that ratio is about 1 into 100,000. Actually, believe it or not, one ice crystal to 100,000 supercooled droplets is actually a good ratio in order to help form precipitation from the Bergeron process. Okay? And you need an effective ice nuclei. Silver iodide has a crystalline structure similar to that of an ice crystal. And remember what we were talking about. Particles that have a geometry resembling an ice crystal can be used to act as ice nuclei. So most cloud seeding products have used silver iodide. It acts as an effective ice nuclei at temperatures less than 25 degrees Fahrenheit. Another particle that can be used to act as an ice nuclei is dry ice or solid carbon dioxide. It has a temperature of minus 108 degrees Fahrenheit on average. It cools the air around it and it helps produce supersaturation. Okay. Now, cloud seeding definitely has uncertainties. Okay, there's still experiments being done to see whether or not it actually helps enable precipitation. Okay, so there is some inconclusiveness. Okay, associated with cloud seeding. Okay, if you're interested, there's some information in the book about some specific examples of cloud seeding, but it can also happen naturally. We're kind of talking about artificial cloud seeding. It can happen naturally downwind of a mountain chain. Under certain conditions, clouds may be seeded by the atmosphere itself, or things in the atmosphere itself, not humans injecting things into the atmosphere. For example, when cirrus clouds or cirrocumulus or cirrostratus clouds form downwind of a mountain, okay, and lie directly above a lower cloud deck, maybe nimbostratus, that's formed as a result of the waves we were talking about, forming waves and clouds downwind of a mountain chain. The ice crystals may descend from the higher cloud and seed the cloud below, and then that can help form precipitation. Notice this snow, this is supposed to be moderate to heavy snow, is falling from this cloud, perhaps nimbostratus, only in areas with cirrus clouds above to seed the clouds below. Okay.